Hey guys, so this is section 4.3, logarithmic functions. So logs are inverse functions to exponentials. And so if you remember, kind of a basic exponential is y equals some base b to the x. And our basic log function is going to be the inverse of this, which is x equals base b of y. And so that's this exponential form of a log function. So it's not that a log is an exponential, it just has an exponential form. If you notice, the x's and y's are swapped, they're backwards. And so that's our inverse form. And because we like to have things as a function of x, we have this other notation for this idea, and that's this log base b of x equals y. To me, logs made no sense without numbers, so I'm going to explain what all these little pieces are doing with an example, because I just think it makes a whole lot more sense if I can actually give it values. So for this first one, we're trying to write this, which is in this form. So let's kind of take a second, and this is the one that I jotted down on paper a bunch of times when I was learning logarithms, just to try to keep straight what all the pieces did. So this reads log base 10 of 100 equals 2. If I wanted to describe in words what log means, it's what power do I raise that 10 to get 100 is what log actually is standing in for. So it's standing in for like a whole bunch of words. What power do I raise the base to get the argument of the log? And then the equal side is the answer. So this would be what power do I raise 10 to get 100? And then the answer is 2. And so you can see the answer is the exponents. So what logs do is they find exponents. And so that's where they're going to be inverse functions to these exponentials. So writing this in this form, the first thing is if you realize the 10 is, if the 10 is the base here, the 10 is the base here. And that's the other two things that are switching places. And so I kind of think of it as 10 raised to the second equals 100. So 10 raised to the second equals 100. I put it underneath there. So 10 raised to the second equals 100. So that's our exponential form. And then the computer made it really confusing as to how to enter the answer. Rather than just having you type that, which would have been totally straightforward, they said write in exponential form this, and then they give you what's A, what's B, what's C. So A matches up with the 10, right? And then B matches up with the 2, and C matches up with the 100. So that's what they're trying to get you to do. I don't know why they didn't just have you type that, but that's the situation. So this one is log base 4 of 1/16 equals -2, or what power do I raise 4 to get 1/16? And then the answer to that is -2. So what power do I raise for 4 to the -2 makes the stuff inside. So 4 raised to the -2 equals the 1/16. So that would be our exponential form. And the A is the 4, the B is the exponent, so that's -2, and C is the answer, so that's 1/16. Okay, so now this time we're given exponential form and asked to go back to log form. So for this I think log, and again the base stays the same, so log base 10, the exponent becomes the answer, and then the answer for the exponential is in the log. So that would be 10,000 equals 4. So I just kind of remember that the base stays the base, and the exponents are the answers in logs, and that kind of helps me get these things switch sides. So kind of when I write it, 10 to the 4 equals 10,000, and if I can write it underneath here, log base 10 of 10,000 equals 4. I sort of think of it as these ones just sort of switching sides. And so here we have log base A of B equals C. So A is the base right there, the 10. B is the 10,000. And C is the answer, the exponent in this case. This one, log. So the base has to be 4. And then the answer becomes the argument, so G. And then the exponent becomes the answer, F. So we'd say A is the 4. G is the B, F is the C. So now we're going to use that idea to solve some little log equations. If I'm looking at this as log base 3 of x equals negative 4, that doesn't really, I don't know, mean a whole lot to me unless I start kind of thinking of it in terms of an exponential. And that's where rewriting this in exponential form can be really helpful, because this way it's not really that clear what I'm shooting for with the x. But if I write it this way, which remember goes 3 and then raised to the negative 4 equals x. So 3, I don't know, I just wrote e. 3 raised to the negative 4 equals x. And now that's something I can work with. Remember, we have negative exponents, we rewrite it as 3 to the 4th equals x, and then 3 to the 4th would be 1 over 81. For this one, I'm going to do the same thing. So 5 raised to the 1 equals x. So 5 to the 1 equals x. So in that case, x just equals 5. This one looks a little bit trickier. So this would be x raised to the 1/2 makes that stuff. So x to the 1/2 equals root 5 over 5. So to undo that 1/2, remember that's like a square root. What I'm going to do is I'm going to square both sides. Because then 2 times 1/2 makes 1, so that gets me my plain x I need. Square root 5 squared makes 5, and 25 on the bottom, 5 squared. And then I can reduce, so that will be 1/5. For number 6, again, I'm going to write it in exponential form, so 6 raised to the x makes that 1/36. So this one, if you can see it's going to be negative 2, you can go just straight there and go negative 2. If that's hard to see, what we want to do is try to get it with a common base, and there's problems where this is going to be a good strategy where you can't just look at it and see. So it's worth knowing either way. So 6 to the x equals, I want to think about how I can get this to be a 6, and so I think, well, right now I have 1 over 6 squared. 36 is 6 squared. And then how do I get this so it's up in the numerator? And the answer is I change the sign on the exponent. And there's that property that says if I have 1 over a to the negative x, that's a to the x. Basically that's what I'm doing here, but in reverse. So it was positive downstairs, and so when I bring it up, it's negative. And when we have negative exponents, we bring them down. We just don't usually bring the positive ones up, but that's what's happening here. And so basically what I have is 6 to the something makes 6 to the something else, so that can only be true if x equals negative 2. So it's a good little trick if you can get a common base. It lets you disregard those and just equate the exponents. And we'll see that in some more examples coming up. So then from the first page we had a couple more things. We have base 10, and what that is if I see a log without a base there, it's an implied 10. So if I just see log x, that's log base 10x. Much the same way that like when we write square root, we don't write the 2, but if we write cube root, we write a 3. This is an implied 2 here, so it's just, if there's nothing, it's a square root. So likewise, if there's nothing, this is base 10. And so then we do when we go to switch this to exponential form, it can be helpful to kind of invent a 10 and go 10 to the y makes x. But you just sort of envision a 10 there. And while I'm here, I'll go ahead and do base e at the same time. So natural log is log base e of x. And so log base e, shorthand for just so we don't have to write a subscript, is ln. It's probably log natural as opposed to natural log. But that is of y. So this is going to go with any e to the x equation. That's its inverse. So then for number 7, we're supposed to simplify these. So this is log. There's nothing there, so that's that base 10 we were just talking about. So this is what power do I raise 10 to get 1,000? And if that's kind of hard for your brain, you can just invent an x and throw it over here and write it in exponential form. 10 to the x makes 1,000. And it might be easier to look at just written in this order rather than in this order. It's the same thing. Either way, it's got to be, x has to be 3, because 10 times 10 times 10 is 1,000. For this one, what power do I raise 32 to get 2? That's a little bit hard to think about, so that's not the worst place to invent an x and throw it over there, just kind of as a placeholder for that. What am I trying to get to? So that would mean 32 raised to the x equals 2, which is the same way as saying what do I raise 32 to get 2. It's just now you can write it better. So 32 to the x makes 2. So this is a good spot to use that common base idea. And 32 is 2 to the 5th. So if I wrote 32, instead of 32, if I wrote 2 to the 5th, x equals 2 to the 1st. And remember, so this, and this are the same. When I have something being raised to a power, that just becomes 5x. They multiply 2 to the 1. So if 2 to the 5x equals 2 to the 1, that can only be true if 5x equals 1. And dividing, I get x equals 1/5. Let's see, for this one, we'll start in our inner parentheses. So log 2, this says what power do I raise 5 to get 25? So 5 to the 1 makes 25, so that would be 2. And then, so this whole thing right here is just 2. And then this is what do I raise 2 to get 2? So 2 to the 1st makes 2. So this is just a big fancy one. For number 10, this one is what power do I raise 9 to get 81? And so that would be 2. And then we have what power do I raise 1/2 to get 2? And that one is maybe a little bit hard to think about, so that's that spot where maybe I invent an x, and it just lets me write it in a form that's a little more comfortable. So that would be 1/2 to the x equals 2. And so then I think about, what can I do to write that with a common base? So if I bring this 2 up, that's going to generate that negative exponent again. So it becomes 2 to the negative x equals 2 to the 1st. So negative x equals 1, and then x equals negative 1. And these last 5 are just to kind of familiarize with the log button on your calculator. So again, if there's nothing here, it's log base 10. And so if you just go log 47.58 in your calculator to 4 decimals, you should come out to 1.6774. If you want to make sure you know how yours is working. If your calculator goes 47.58 and then the log, that calculator is going to make you really unhappy. You might think about getting just like a scientific one, but a newer one where it's log and the number, because the style where you go number log are really hard to put stuff in on. This one is natural log of 10.49. So again, this is just so you find your natural log button, then type this in and make sure you know how it works. So 2.3504. For number 13, so this actually has a little bit of math to it. This is, since there's nothing here, it's an invisible 10. So this, to solve this, is really 10 to the 1.285 equals x. And then if we throw this in the calculator, I got x to be around 19.2752. This one, natural log, this is the same thing as log base e of x. And so here I can say e raised to this value makes that x. And then just chunking that in the calculator, I got 7.9645. And then this last one, I have ln x equals log 13. So log 13 is just a number. So it's 1.1139, goes on forever. And then we're basically doing e to this value equals x. And then through that in calculator, I got x to be 3.0463. Okay, and then the last thing in this section is running some properties of logarithms. So these are the ones where it's sort of the, it's like saying the square root of x squared. You know how that ends up being x? Let me write what I just said. So if you have the square root of x squared, the root undoes the square. Or likewise, if I had root and then squared, same idea. That's kind of what these properties are doing. So we're raising something to a log, or we're taking the log of something with an exponent. So it's the same kind of do and undo itself. So when I have this one, let me write it a little bit bigger, b and then log to the base b of x. So when those bases are the same, and this is raised to that power, it just comes out x. And that's kind of what you're going to see with all of these. E ln x, x, because this is really e and then log base e of x. So it's sort of doing and undoing itself. I think it helps with this to see just maybe one little example over here. I'll just do it as kind of scratch work. Say we had 10 log base 10 of 100. And so that, remember that log base 10 of 100 is what power do I raise 10 to get 100? And that would be 2, right? So log base 10 of 100, that equals 2. So then that's 10 squared, and 10 squared gets us right back to the 100. So what do I raise 10 to get 100? 2, and then 10 raised that same power right back to 100. So that's the idea behind all of these properties, is they're just going to kind of get us back to what we put in, because it's the inverse of doing it and doing itself. So here we have e and then ln root 5, and so that's just really going to be root 5 because the base of the log and the exponential are the same. So that's this one right here. For this one, if I rewrite it as natural log, and then instead of 1 over e to the fourth, I'm going to write it as e to the negative fourth, and then that makes it look like this property right here, ln e to the x equals x. So this would just equal negative 4. This one's the same as that, it's just already set up, so probably should have that one come first. So this one is just 5. 19, so that looks like this right here. So the base of the exponential and the log are the same, so it's just the argument of the log, or the 11. This one, it's this one, and how the x's are both 7. Here the bases, it's a little confusing because this is x here and this is the base here, but basically the base of the exponential and the base of the log have to be the same, so this has to be the same as this, so x equals 5. And then for this one, ln e to the x is really just x, because ln e to the x is x, so x equals 9. Okay, so number 22, log base 7 to 12, that's saying what power do I raise 7 to get 12? And so there's a couple of things that could have you do with that. I think there might be a question on the homework that has write as a ratio or something of natural logs. And so that would be ln 12 over ln 7. And what this is our change of base property. So, you know, it's what do we raise 7 to get 12 is not an easy number. And so we do this change of base thing, so we can change it into base e or base 10 and then throw it in a calculator. So I think there might be one on the homework that asks you to write it like this. And then if it asks for a decimal, you could do ln 12 over ln 7 in a calculator, and that comes out to about 1.2770. Had I done log 12 over log 7, it would still come out to the, oops, that should be a 7 down there, sorry. It would still come out to the exact same thing. It's not that ln 12 and log 12 are the same thing, but the ratios of the logs are the same. So much the same way that if I had 12 over 6 versus 8 over 4. 12 over 6 is 2, 8 over 4 is 2, but it doesn't mean that the numbers are the same, but the ratios are. So I think, like I said, I think there might be one that asks for in this form, and maybe some that ask for the decimal. This is just a little simplify log 10, so remember that we know log 10 is the same as log base 10 of 10, so what power do we raise 10 to get 10? It's just kind of a fancy version of 1, and I think that's over here somewhere. It's on one coming up. And then ln1, same as log 1. Oh, yeah, this was it. Sorry, log base b of b equals 1. And then if we have the natural log of 1 or log of 1, those are just 0. Because that's saying, what power do I raise e to get 1? So e to the x equals 1. And remember, anything to the 0 makes 1. So that wraps up, I think, 4.3.